can't believe I ate that whole thing.
You ate it, Ralph.
I can't believe I ate that whole thing.
No, Ralph, I ate it.
I can't believe I ate that whole thing.
Take 2 Alka-Seltzer.
For headache and stuffy, upset stomach, no aspirin or antacid alone relieves you in as many ways as Alka-Seltzer.
Modern medicines for modern aches and pains. We're told to take so many so often, you'd think one might spell relief.
How do you spell relief?
I spell it R-O-L-A-I-D-S.
It's widely known that research chemists and physicians spend years testing medications and collecting data just to make sure that your relief is safe as well as effective. But you may not know that mathematics can be used in this process. How? Well, to understand that, what you need is a prescription for calculus. Driving while intoxicated can be lethal, but accidents like this can be prevented using a little common sense and simple mathematics. We know from our research that after entering through the mouth, alcohol is almost instantly absorbed into the bloodstream, circulating then to the brain and other body organs and tissues. Given the legal limit for DWI is 0.08, we can easily create a mathematical model which would tell us how long to wait before we reach the legal limit. Graphically, the process looks a lot like this. We know from our data that absorption comes first and fast, with elimination beginning shortly after, and following a distinctive, predictable, and constant rate of decline, about 0.02 of a gram per deciliter per hour. We have collected data on a number of people of average height and weight and have discovered that when they drank 6 ounces of alcohol in 1 hour, that's roughly 6 bottles of beer, 4 shots of hard liquor, or 4 5-ounce glasses of wine, their blood alcohol concentration was about 0.11. Our model looks like this. C of T equals the concentration at peak, C peak, less the elimination rate, 0.02, times the waiting time, T wait. Setting C of T to the legal limit, 0.08, we can solve for the time it takes to get under the legal limit. The answer is 1.5 hours. Do all drugs follow a similar mathematical model? If so, then our work is simple. Let's find out.
We're at your location with a 63-year-old white male complaining of substernal chest pain.
Blood pressure is 165/80, pulse rate of 88 and irregular. We have a possible TIMI patient here.
There are many pharmaceuticals used in the treatment of cardiac problems. Again, we have gathered some data, this time on digoxin, a typical drug used in the treatment of cardiovascular disease. Let's see if we can find a mathematical model which can be used to determine safe, effective dosage levels for our patient. The data we're using is actually higher than what is administered so that you can clearly see the pattern of elimination. Let's graph the data. Note that unlike the alcohol model, digoxin doesn't leave the body at a constant rate, so our previous linear model won't work. We need another model. Where do we start? Well, this graph looks somewhat familiar. It's an exponential curve, and we may have seen it plotted for radioactive decay. Let's start with that. Let's assume that the rate of elimination for digoxin is similar to that of radioactive decay, that is, proportional to its concentration at any point in time. Therefore, we need to find a model that will provide us with a constant for the percent change of digoxin in the body. Let's see if the classical mathematical model for exponential decay fits. Here it is. In our case, this says that the rate of change is directly proportional to the amount of digoxin in the bloodstream. Using the power of calculus, we arrive at the following mathematical model. C of t equals C of 0 multiplied by the base e raised to the power minus kt. Let's test our model to see if it will work. First, let's rewrite our model like this. Now, taking the logarithm of both sides, we get this expression. If our assumption of exponential decay is correct, a plot of the log of C of t over C of 0 versus t should be a straight line with slope minus k. Our model looks good, but in order to use our model in a practical way, we need to find k using the data. Now, let's determine k. A quick way to get our constant k is to take the slope of the line. We get that by using the equation slope equals rise over run. Filling in the numbers, we arrive at minus 0.357, or rounding it off, minus 0.36 for minus k. So k, our constant for the percentage change of digoxin in the bloodstream, is 0.36. While it's taken a while to generate this model, we can now use it to solve an amazing variety of problems. For example, time between dosages. First, let's assume that the highest dosage at which digoxin is safe is our initial hypothetical dosage, 3.25 milligrams, and the lowest effective concentration is 0.85 milligrams. How many days should our patient wait before taking his next dose, assuming that the loading rate is almost instantaneous? Okay, here's our model. Plugging the numbers into our model, we get and solving for t, we get approximately 3 3/4 days between dosages. We could use our model to find the initial dosage by taking a blood sample, finding out the present dosage, and knowing how long ago the medication was administered. Or we could find the current amount of digoxin in the bloodstream if we knew the loading dosage and how long ago it was taken. But what about a tougher, more realistic problem? How can we determine the best maintenance dosage and medication schedule for our patient? One that is safe, effective, and convenient. Well, here's a graphic display that demonstrates one such solution. Here's another. Here, still another. But what's the best solution? We'll leave that work for you. It should be easier now that you've got a prescription for calculus.